MDM4U 4.5 applying Pascal's method. So the first thing that we're going to do is an investigation. Let's look at this problem. How many paths from the top bucket to the lower level are possible? So if we have water trickling down into this bucket and it can go either left or right, let's assume that there was a ball that was landing into this bucket and went either left or right. So it could have went maybe left and then fallen right, maybe fallen right again. And let's think of how many different ways could we end up getting to the bottom. So you can pause this video and try to figure it out on your own if you'd like to investigate. But let's take a look at our lesson, 4.5, applying Pascal's method. Pascal's method. The number of paths you can take to get to a point is the sum of the number of ways you could get to the connected points. So this Pascal's method is a way to count paths, but what we need to focus on is the number of ways in which we can get to each point. Now there's only one way to get to the starting point, and if we were to go to the right side, the only path that would have led to that was going down and to the right. So there's one way to get here. And similarly, we could have dropped a ball here. It would maybe go to the left-hand side, and there's one way to get to that point. Next, let's focus on this bucket. In order to get to this point, it would have fallen to the left and then to the left. So there's only one route to get to that point, or one path. This next bucket, we could fall down to the left and then to the right, so that's one path, and then another path is to the right and then to the left. So there's two paths to get to this position. Lastly, in this row, this bucket, we can only fall right and then right, so therefore there's one route to get here. Next, this bucket, we would have to the left, and to the left. There's only one way to get to this position. Similarly, in this case here, we would have one way, left, left, right, left, right, left, and right, left, left. Now, can you spot what's happening? If you can recall our last lesson, what does this look like already? Notice that there's the relationship of 1 plus 2 is 3. Each bucket is the sum of the previous points. Now in this case, we end up having this just like Pascal's triangle, because in a triangular formation. So our answer is, to get to the bottom, we can get it in 1 plus 3 plus 3 plus 1 ways. And if you remember the row sums, this is the third row, because row 0, row 1, row 2, this is 2 to the power 3. So that is the number of paths that are possible to get to the bottom position. So let's apply this in a more abstract sense. Let's picture we were moving down a city block, and we were moving from point A to B. And how many routes are possible from point A to point B if you can only travel east or south? So that would mean to the right or down, because to the right or down advances you towards the position B if you start at A. So we're going to use this right hand side here. In order to get to this position, there's only one way. You start off here, but to get to this position, and there's only one way, because you would travel east or to the right. So there's one way to get to this position. And if I were to look at this corner, or this vertex, there's one way to get here because you could only go down. So let's focus on this position. I could go to the right and down, or to the down, to the down. Go down and then right. So there's two ways to get to this position. So because of the constraint, we can only move right or down. Notice that there's only one way to get here because you travel right and then right. Notice that that's the same for each of these positions. For the third position, I could only go right, right, right. So I'm going to reveal that there's one way to get to any position here on this first row. Now notice the following. I'm being consistent in the way that I'm writing down the number of paths to a certain node or point. I'm going up to the right of it. As we go down, there's only one way to get to this position. Down and down. Similarly here, there's only one way. Down all 3 times and then all 4 times. So, I like to think of this as the frame of our problem. We're going to see how Pascal's method applies throughout the entire problem, but it's nice to have this outside frame to start with the next steps. So, let's review the definition of Pascal's method. The number of paths you could take to get to a point is the sum of the number of ways you could get to the connected points. So let's apply that in this context. This point, you could get to the connected points. This is connected because you could approach it from this side and you could approach it from this side. So 1 plus 2 is 3. Let's just check down, down, right. 1. Down, right, down. 2. Right, down, down, 3. Those are the only acceptable ways to get to this point given the constraints, moving right and down only. So that confirms that we have 1 and 2 adds to make 3, and we can do that for each of these positions. So 1 and 2 makes 3. And let's start our next row. Notice it kind of looks like Pascal's triangle at an angle, so we'll go in order. Let's think about this position here. This position we can't determine yet because we have the number of paths connected to from the left side, but not from above. So you always have to know the number of paths that are approaching a point before starting at this point. We must go here. 1 and 3 makes 4. And then 1 and 4, now we have both connected points, makes 5. Good, we're going to continue forward. 3 and 3 makes 6. 4 and 6 makes 10. 5 and 10 makes 15. 3 and 1 makes 4. 6 and 4 makes 10. 10 and 10, 20. 15 and 20 is 35. 4 and 1, 5. 10 and 5, 15. 20 and 15, 35. 35 and 35 is 70. 6 is 5 and 1. Next is 15 and 6, 21. 35 plus 21 is 56. 70 plus 56 is 126. 6 and 1 is 7. See the advantage of writing the outer frame. Then 21 and 7 is 28. 56 and 28 is 84. And 126 and 84 is 210. The total number of paths is 210. So you can see that this counting method is advantageous because we would never count these out individually. The difficulty increases. Let's take a look at this problem here. Notice that in our last example, all of the blocks were completely, we had a triangular formation. So this is actually a snapshot or a portion of Pascal's triangle. But we need to be able to be flexible and adjust. Notice that there's gaps here. Let's see how that affects our problem. So I've just copied this image here for our solution. And we start here. There's the outer frame. There's one way to get here, so there's one way to get to each of these positions, and that is simply going to the right every single time. And similarly here, to get to this position, there's one way. Notice that I'm consistent in always writing to the top right. Now, for whatever reason, there it is. So we have the connected path, the number of ways to get to each of those connected points. So we can say that there's 2 ways to get to here. Down, right, down. Similarly, we have the connected paths, so we can add them to get 3. And here, 2 and 1 makes 3. I'm going to avoid challenges at all costs. 1 and 3 before moving forward. Notice that that is a point itself. 1 and 3 makes 4. Similarly here, 1 and 4 makes 5. So 3 and 3 makes 6. We haven't run into any issues yet. 3 and 1. And 6 and 4 makes 10. 4 and 1 makes 5. 10 and 5 makes 15. Notice here there's only one entry point, so it's 10. Next, 5 and 10 makes 15. 10 and 15 is 25. 15 and 25 is 40. And notice that we can't do these points because we don't have the connected path yet, or the number of ways to get to the connected points. So we have to do this first. There's 15 ways to get to here, because if there's 15 ways to get to this point, we can only move right to get to here. There's only one entry point for 15. Remember, we're constricted to moving right and down. So 15 in this position. This will be 16. 25 and 15 is 40. 40 and 40 is 80. We have 40 plus 16 is 56. 80 plus 56 is 136. 136 paths total. Good luck.